with PIC microcontroller peripherals. So in the last class we have seen about the introduction to PIC microcontroller and what features, in which features it is different from 8051 microcontroller is what we have seen. Today's class what we do is, if you want to use PIC microcontroller, you have to know what are the peripherals available, and using those peripherals how can you perform different tasks. So now if you try to see the onboard peripherals, the MCU microcontroller unit peripherals, if you try to see, you have digital IOs, okay, so digital input output bits, and you have timers, so on-chip timers. So architecture is what we have seen in the last class, like the RAM and ROM. Memory organization is what we have discussed in the last class, and internal architecture is what we have seen in the last class. So now in this class what we do is, let us try to discuss the peripherals available with the PIC microcontroller, and then how to do programming of those is what, in general is what we'll try to discuss. And you may find difficulty here, when you are going from one microcontroller to another microcontroller. Now let us try to take, if you are going with 8051 Intel microcontroller, so then you have to see its instruction set, right? The instruction formats and addressing modes would be little different when you try to compare with PIC microcontroller. And when you try to see Atmel microcontroller, then that would be different. So in general, if you have a knowledge on how one microcontroller to another microcontroller, conceptually it is different, then a specific microcontroller when you are dealing, it is very easy for you to understand the terminology related to the microcontroller. So what we do in this class, the peripherals available with the microcontroller is what we try to take up, right? And then we try to see the timers, and then come parallel slave mode and all, and interrupts of PIC microcontroller, right? And once we know those things in detail of going using the register level, like how we have seen 8051 with registers like SBUF, SCON, PCON, like that, the registers which are available with microcontroller 8051. Up to that depth I am not going, right? Because once you have the knowledge on the common things, so then you can go ahead with. Otherwise, like detailed one to another one microcontroller, when you go, the registers will vary controller to controller, and you have to learn. That is the case. So the popular microcontroller is what we are discussing now, PIC microcontroller. So if you are using this, if it is a choice for you, then definitely you have to go in detail. So one example I will try to show you, and then you can go ahead with it. So now let us discuss the PIC MCU peripherals. So then coming to the peripherals, if you want to interface your PIC microcontroller with the external world, then you need to use the port pins, and with detail is what we will try to see. So then onboard timers and onboard on-chip, you can say on-chip AD converter and comparator, and you have a facility here, you can extend the ports, which is parallel slave port, and then the interrupts available with PIC microcontroller is what we will try to see in this particular class. So now coming to the 16F877 microcontroller, which we are dealing with now, has the following digital I/O port pins. Right, the following digital I/O port pins available. So port A, port B, port C, port D, and port E. So port A are 6 bits, and port B are 8 bits. Port C are 8 bits. port D are 8 bits, and port E are 3 bits. So total 33 pins are available. So the total digital I/O pins available are 33 bits. See, this you can compare with the Atmel microcontroller 2, which is which you are using widely in your Arduino board, which is widely you are using. So now let us try to take that. Now let me show you the details so that you can have a comparison of this. Yeah. So this is what another popular architecture point of view, the controller. So this is Arduino Uno R3. And first of all, how many things you are using is different. But now Arduino Uno board, if you try to see, this has the digital pins like, digital I/O pins like this, here. This is Arduino Atmel family. So the digital I/O pins available are, these are the pins available, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 pins are digital I/O pins. Because why I am showing you this is you are very familiar with the Arduino boards, and it's very easy to use Arduino board. So the digital I/O pins which are available here on the Arduino pin are these are the things like pin number 2, 3, 4, 5, 6, 7 and 8, 9, 10, 11, 12, 13. So you can use these pins to interface your external world. So this is Atmel Atmega 328. This is Atmel, but PIC we are trying to discuss. So in PIC microcontroller, when you try to see, so here you have the I/O pins, the digital I/O pins, like how you see in your Arduino, right, which is of Atmel microcontroller. So port A are 6 bits, port B are 8 bits, port C are 8 bits. So port B, C, D, they are 24 pins, and port A has 6 pins and port E has 3 pins. So total 33 pins are digital I/O. But whereas now see comparatively one controller to another controller when you try to see, and here when you try to see the Arduino board, it has different I/O pins, but you are using these pins dedicatedly for digital I/O. You can understand how you are going to connect the external world to the controllers. And these are analog I/O pins. Analog I/O pins are A0, A1, A2, A3, A4, A5. So 6 analog pins you can connect. 6 analog pins you can connect, and then these are the digital I/O pins you can. And then here, serial transmission point of view, you have serial in and serial transmission, and then receiving the bits can be done by using this. Okay, so 1, 2, 3, 4, 5 all PWM pins here. 5, 6 are PWM pins. So this is in detail it is brought out like an controller point of view, right? As easy to use on board and everything. So it is very popular, and you are using this. So I am trying to compare what exactly is digital I/O pins and analog I/O pins. So digital I/O pins and analog I/O pins. Here if you try to see for PIC microcontroller, so here you have digital I/O pins are 33. Port A, port B, port C, port D and port E. So the total pins are, right, so the total pins are, so now here if you try to see, so this is what your Arduino board which I am trying to show you. Right, so here you have the digital I/O pins, right, digital I/O pins, and here you have your analog I/O pins. Right, so now we are going to discuss, right, these are the features. So digital I/O, timers, A/D converter, comparator and all. So the port pins are 33 port pins are available. So that you can list or identify here. So now if you try to see RA0, RA1, so this is RA0, RA1, RA2, RA3, RA4, RA5. So these 6 pins are port A, and port B are 8 pins. Port B are 8 pins. So RB0, RB1, RB2, RB3, RB4, RB5, RB6, RB7. So these are port B. So these are 6 pins are port A. Right, and port C or 8. So 8 pins are port C. So PC7, PC6, PC5, PC4. These are 4, and RC0, RC1, RC2, RC3. So these are port C, 8 pins. And port D, four, and port D, 2. So these are D. And port E, RE0 and RE2. So these are E. So port ER3, port AR6, port BR8, port DR8, and port CR8. Right, port CR8. All right. Okay. So these are the digital I/O pins available, as we have seen in Arduino board. So Arduino, here you have pin 2, two, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. So these are the digital I/O pins, where you can send only ones and zeros are. But whereas an analog, okay, so analog you have this 6 pins available, A0 to A5. Because you are very familiar with this, you can understand easily what exactly digital I/O. So that's what I'm trying to show you. In the PIC microcontroller has these many ports. So now, once you have the digital I/O pins, you can connect the external devices like LCD, keypad, or any sensor. You can connect it to PIC microcontroller by using these particular pins, digital I/O pins. Now, the sensor connection, that sensor connection depends upon here, how many you have analog I/O pins. So We are trying to see the digital I/O pins and analog I/O pins used for this 16F877 microcontroller is. So AN0 and AN1 and AN2, AN3 and AN4, AN5, AN6. So these are the channels available. AN6, AN7. So 8 analog channels, 8 sensors you can connect to the PIC microcontroller using the on-chip A to D converter. So on-chip A to D converter, the pins are this 1, 2, 3, 4, 5, 6, 7, 8. So you have 33 digital I/O pins are available, and here you have 8 analog ports available. 8 analog ports available in which you can connect your sensors to PIC microcontroller using these particular pins. All right. Okay. So then, now let us try to see, like when you are trying to connect the I/O devices to PIC microcontroller. So how can we configure or initialize these particular ports? So as we discussed up to now, coming to the ports, if a port is acting like input port, then it should have buffer. So yes, buffer. And if any port pin it has to act like an output port, then it should have latch. So a simplified diagram of PIC 16F877, if you try to see, here you have data direction latch. By setting this, any particular pin can be made output pin or input pin. So if you want to make the pins, by default, when you switch on the microcontroller, each pin is initialized as input port. Means to safeguard your pin from the external world. So by default, it is initialized like input port. So now if you want to read the data from the external world, so then if buffer is in between, so then easily it can isolate your external devices to the microcontroller so that the pins are getting safe. So now you can make by writing a bit in your TRIS. So if you write 1, that means then this particular bit, then this particular thing can be used as input port. So to configure so to configure 87F, to configure F877, input port we have to write one. And if you want to configure this as an output port, then write 0. So in 8051 also we have did the same. To configure the port as input port. So when it is input port, then you are writing 1. So when you are writing 1, so this is simple, it's a latch. So when it is 1, then you are writing 1 here. When it is 1, right. So this driver circuit will be disabled. Right. And the bit can be, you can read the data. So this, you can read the data by using this particular latch to CPU data access. Is it all right? Okay, so and if you want to write data, then you will write here 0. Right, so when you are writing 0 here, then as usual, the same thing can be available here. This is on. When it is on, then this bit is connected to output. So this is an equivalent circuit of the 16F877 ports. It's only equal circuit, not the exact circuit is. All right. Now, and I'll try to show you 1 or 2 examples where you can use PIC microcontroller for different applications. Right. So here, when you are trying to interface external devices to PIC microcontroller, so try to see if you are going to use it as input, then write 1 in TRIS. And if you want to use it as output port, write 0 in TRIS. Okay. All right. So this is about the port, the digital port pins available with PIC microcontroller and analog pins available with PIC microcontroller. And interfacing point of view, you will try to see. So you can take up an example like how can you interface a keyboard with 16FF. You will find n number of projects. So covering this, because I covered this in 8051 microcontroller. So you can similarly try with this. So now if you try to see n number of so 16F877 keyboard. So then you can see this, like how it is interfaced and all, the different codes and all, you can try to see. See here you have the keypad. So this keypad is connected to 16F microcontroller. Right, so then this one, yeah, so this you can try to see here. So this is so this keypad is connected. So 12 keys, 4 rows and then 3 columns. So this I discussed in detail. The same thing you can go ahead with. Only the thing is the controller is changing. All right. So now, right, they are connected to 7 pins are connected to D port, and now this is connected to B port. So the B port are B0, 1, 2, 3, 4, 5, 6, 7. So the LCD is connected to B port. So 8 port. So here, this is the simple connection of your keypad with 8051. sorry, 16F877. Right. So you can do the similar, the similar interfacing if you have the 16F877 in your laboratory. Right. And then you can try using of it. Okay, if you can try using of it, and you can start writing code by going through the instruction set, or you can use C language. Okay, C language for programming 16F77. Is it all right? So these are the connections, once you know the port pins and all, right, so it's very easy for you so to do the interface. Now the logic should be same, but instructions should be varying here in this case. Okay, all right. So you have n number, if you can see the coding part and all, so how this can be used as input port and output port. Now if you try to see the coding part, the LCD here is 16 and all the connections, and we have discussed in detail, and now this is what the code. So CCSC compiled for big microcontroller, if you try to see. Okay, so the logic of interfacing would be the same. Little bit, the instructions, little bit instructions will be varying. So this you can try. This is what simple example. Right? If I just go through, like I can easily, just now what we have discussed to make so this is to make a port, input port or output port, we have to write specifically in your TRIS bit. That's what we said, right? So now let us try to take, keypad is connected to RD3, RD2, RD3, RD4 and all. So for the D. So then, right, so column scanning and all you will be doing. So here, so TRIS, if you try to see in this particular code, so TRIS, if you try to see here in this particular code, so the bit TRIS, right? So setting of this TRIS pins of port D. So now if you try to see here, these are 88. X stands for hexadecimal. So TRIS C1, C2, C3. So C3 is what you are making. So column pins and all you are making 1, 1. So 88. Dot 0, dot 1, dot 2 and all. So you are trying to set this port to D, right? This is R1, R2 and all. So they are rows and these are columns. C1, C2, C3, these are the columns. So if you are going to use this as input, okay, so if you are going to use this as an input, then you have to write 1 into it. 88 is the address, dot 0 is that particular pin. Okay. So this is how you assign bit C1 08. C2, C3, R1, R2, R3. So that you are going to make it as TRIS. All right. And LCD also, we will try to make it as 0 or 1. So this is resistor select and enable. Okay. So the same coding part and all you can apply to PIC microcontroller too. Initialization, if you know exactly this particular hardware, if it is there in your mind, like which is input and output, so how to scan rows, any keys pressed or not is the first, then scanning your thing, like columns and scanning your rows, then identifying that particular key, and that has to be displayed on the LCD. So this can be easily seen, if it is any microcontroller, when hardware is in the mind, then anything you can do. All right. So this is about the big microcontroller and then bigger microcontroller port pins. Right? Okay. So then now let us move to the next topic, that is the next feature available with 805. Sorry, big microcontroller is timer. So now let us try to see what exactly the timer does. So timer, it generates different timing delay signals. Right. So if you want to blast a bomb after half an hour, so you have to need to generate a delay which is of half an hour. Right. So thing is, you can generate different timing waveforms using timers on chip of the microcontroller. So now let us try to see the generalized working principle so that the same thing can be extended to PIC. So this is one where you can generate different pulse widths for the big microcontroller, and which we are using it as a timing application to generate different delay times for different applications. And next one is to count the external sequence or events. So to count external events, you will be using the external events as a clock. When it is in a timing, so when it is used as a timing of application, right? When it is used as a timer applications, then your internal clock cycle is used as the clock source. And when it is used as a counter, so when the timer is used as a counter to count the external sequences, so then external pulse will act like a clock source. But when it is using as a timer to generate different timing sequences, then instruction clock can be used as, okay, so the internal clock can be used as the clock source. So then what is this prescaler or clock divider? So you may have on-chip timers of 8-bit, you may have on-chip timers of 16-bit. So if you have 8-bit timer, so then 2 power 8, okay, 2 power 8 is how much? 256, 256, yes, 256 times you can go hardware. So when the counter of 8-bit, when it starts counting from 0, 1, 2, 3, 4 and all, right, 4 and all, it counts maximum up to 256, right, 256, and after 256 it becomes 0, it rolls to 0, right, it rolls to 0, and if it is of 16-bit, so then 65,536. Okay, 65,536 it will count, right? And then 65,536, is that correct? Yeah, 65,000. So here you have yeah. So 16-bit. So once it starts counting from 0 to that particular count, then it will tries to make the overflow flag 1. Okay, overflow flag 1. So that is done by using the binary counter. So this is common for all the timers. You can apply the same thing with timers. So then here you have, so the clock is connected to the internal clock or external clock. That depends, we are using that as a timer or a counter. So when you are using it as a timer, the clock is connected to its internal clock cycle, clock signal, right? And then if it is a binary counter, if it is 8-bit counter and counting, so it will count from 0 to 256, and right, 0 to 255, which is up 256 counts, then it will try to set the flag high. So it will try to set the flag high. Okay, right. So then now if the counter has to start not from 0 to max, if it is have to start, if it is starting from a particular value, so it has to be preloaded with certain value, so that is prescaler. means dividing your clock signal, okay, as to reduce the count. So the case is, now let us take time. This timer is used. This timer of 16 PIC microcontroller is used as a timing application. So then the count register mostly commonly used to operate deriving from the internal instruction clock to form a timer. So the signal runs at 1/4 of the clock frequency. So the signal runs at 1/4 of the clock frequency. That is, one instruction takes 4 cycles to execute. So therefore, a 4 megahertz clock, the timer counts in microseconds. So the timer counts in microseconds. That means 1 megahertz instruction clock is what you try to get. So now let us take 1 megahertz is what your clock frequency. So when you are using it as a timing application. Right. So then if it is 8-bit, then it will going to count 256. But now if you want to modify the count period, okay, this is what important. If you want to modify the count period, so then the time register can be preloaded with the given number. So the timer register, can be preloaded with the, so we will be preloaded with the given number. So if you take an example, if an 8-bit register, like if an 8-bit register is preloaded with 156, okay, if it is preloaded with 156, so then a time occurs after. So 256 minus 156 means 100 clocks. So many timer models allow automatic preloading each time it is restarted. So in which case the required value is stored in a preload register during the timer initialization. So this is what your preload or prescaler is what we can try to say. So the prescaler, when you try to divide, so then you can take it this prescaler value. So the top derived value as 1, 2, 4, 8, right, 16. So 16 times you can divide your clock signal. So that is what prescaler is. So the 877 has, now coming to the PIC microcontroller, this is what your general timer counting application, right? And then there you have a capture register which captures the binary counter counting sequence. And if you have a compare, and here you have a compare register, so then when binary counter, when it is counting, always it compares with the register value, and once the counting is same, so then it sets the flag register, right? It sets the flag register. So then here you have prescaler, and some timers have post-scalers too. Right, so the timer overflow or timer out flag is set to 1. So match flag is 1, and then that particular timer overflow or timer out flag, so it is set to 1, indicating the timer is need to be serviced. Okay, so this is what the general timer operations. Now let us try to see in the in particular 877. So 877 has 3 timers. So 3 timer counter registers, The same thing with Atmel family too. The same thing with Atmel family. If you try to see the timing sequences and all, yeah, so same thing can be, you try to see with so PWM, yeah, so this is a PWM pulse width and all. I want to show you this, but okay, so here, any generalized the timer operation, you will be having a clock source has to be selected from internal clock or external clock, and you have a prescaler by which you can divide the count value, so which is generally it can be done in terms of 1, 2, 4, 8, 16, right? 16 or 32 times, you can divide the clock frequency, right? And then once the count is done, in this example, if you try to see, So if it is preloaded with 156, so then the timing occurs, after 200 clock cycles only. So then the timer makes the timer flag bit high. Okay, timer flag bit high, which generates an interrupt to the controllers, right? And the 877 has timer 0. So timer 0, it has 3 timers. Okay, it has 3 timers. So then it is timer 0, has an 8-bit counter and 8-bit prescaler. Okay, 8-bit prescaler. So 8-bit prescaler means 256, up to 256, like 1 by 2, 1 by 4, 1 by 8, 1 by 64, 1 by 128, 1 by 256. So 8-bit prescaler it has. So it can be clocked from the instruction clock or an external signal applied to RA4. So the prescaler can also be used to extend the watchdog timer interval. Okay, watchdog timer interval, in which case it is not available for the use with timer 0. So timer 0 is an 8-bit counter with 8-bit prescaler. And coming to the timer 1, it has 16-bit counter and a prescaler and can be clocked internally or externally as per timer 0. So it offers capture and compare modes of operation. So timer 1 offers capture and compare mode of operation, which is very helpful for you to generate pulse width modulation signals. And timer 2 is another 8-bit counter. So timer 2 is another 8-bit counter, but has both prescaler and postcaler. So postcaler up to 1 to 16 and compare resistor for period control. So this is timer operation of 16F877. And applications has to be seen, like how you can generate a pulse width of a duty cycle 30% or 60% or 80% using this. So you can easily get it through. So you just Google it, or you can easily get, like 16FF 16F877A PWM. So how to generate PWM using PIC 16F877. So when when on time is more, LED will be glowing more. When off time is small, then it will be for a smaller time it will be glowing. So if you try to see, it has capture resistor, compare resistor, PWM resistor. Okay, it has 16-bit capture resistor, 16-bit compare resistor, 10-bit PWM resistor. So then the port pins are PC.2, PC.1. So the control resistor related with this one is this CCP1 con and CCP2 con. And duty cycle resistor you have control resistor, duty cycle resistor and period resistor. So 3 resistors. And coming to the PWM working point of view, so you have to load these things. You can go in detail of this, how to generate different duty cycles using PWM. So you have duty cycle resistors, okay, duty cycle resistors, and like you can make it as in slave mode. And here you can have a comparator, so up to that particular comparator. So you can relate the working of this using this particular, you can relate the working of this using this. This is generalized working. So here you have capture register, compare register. So prescaler and postcaler. Alright, so the same thing you can try to find out here in terms of PWM, how it can be generated. So the duty cycle is on period to off period, right? So on time, off. So then, so these are the registers related with timers and counters. So CCP is used to configure the CCP module for capture, compare and PWM operation. So three modes of operations of a timer. So now let us take this PWM, and this register holds the 8 MSB bits of PWM, and lower 2 bits will be part of CCP register. And TMR2, so this is free running counter which will be compared with CCPRIL1. So little bit hardware you need to see. So this is CCP con, and individual bits you can go further. So this least significant bit. So when these bits are 0, 0, 0, 0, right? So this is from CCP M0 to M3. This is capture, compare, PWM disabled when it is 0, 0, 0, and when it is 0, 1, 0, 0, capture mode and every falling edge. And every falling edge you capture the value of your counter. 0101 is capture mode and every rising edge. Okay, so like that you can see a little bit hardware and you can go further. So the steps to configure PWM is, so you configure the CCP1 module for PWM operation and set the PWM period by writing to the PR2 register. Set the PWM duty cycle by writing to CCPRIL register and CCPCon bits. And make CCP1 pins output by clearing the TRIS, the 2 bits, and then set the TMR2 prescale value. Right, so this is what the steps you need to follow, and then this is what the simple code of configuring this in timing PWM operations. So this is what the simple, right, so simple pulse width modulation. So pulse width modulation generation by using this. It is similar, what I am trying to say is once you know the concepts in mind, and then you can have how it can be done in a particular microcontroller. So that is what important is, right? So then you can take, this is simple program, right? Simple program, how it can be used to generate PWMs, right? So this is duty cycle of 20%, on time is less, off time is more. 20%. Then this is 40%, T on and off, T off, both are, so T on is more, T off is less, 60%, and then this is 80% duty cycle. Right, so T on by T on plus T off into 100 will be your duty cycle. Right. So this is what your logical diagram. So how can you make this particular bit to generate PWM? And this is available, this PWM is available, 6 pins are available for PWM in your Arduino board. This PWM pins are available, so 1, 2, 3 pins, 3, 5, 6, 9, 10 are PWM pins. This is readily available, cheaper, 250 rupees, 300 rupees, your Arduino board is available. But the same features are there with 16F677. So it has 3 counters or timers, timer 0, timer 1 and timer 2. So timer 0 is with 8-bit counter, timer 1 is of 16-bit counter, and timer 2 is an 8-bit counter with prescaler and postcaler facility. Right. So how it can be used to generate PWM signal is what you can go through. A number of examples available. Right. So then coming to the ADC operation. So PIC microcontroller has 8 analog input pins. So now if you have this analog to digital converter in mind, then how to use and how to write algorithm, like how to write your pseudo code, easily you can go ahead. So you can write your algorithm first, then those algorithms you can convert into program. So in 16FF you have 8 analog input pins, as I have shown you, and you have to select any one of this by selecting the select lines. So to interface this, right? So analog input pins, right? So then if ABC or 000, 0th will be selected. If 001, then next one, 010, the next one. So like that, out of this pins available, means your wherever signal is connected, you can select any one of this. And once it is selected, then you have to give start of pulse. Then you have to see the end, the end of conversion. Once the conversion is done, this end of conversion will become high, means conversion is done. So then you have to give a pulse on the buffer to bring out the bits of analog to digital converter. So this is what simple operation, and I discussed this very clearly in A2D converter interface into 8051. Okay. So the same thing, it can be extended, easily, you can extend the same concepts to, so sensor interface. So sensor interface into 16F877. So any sensor, just go in detail, right? Because I already discussed this, so I'm just trying to give you an idea. So this is, to like human presence there or not. So PIR sensor, right? So how it is interfaced to your microcontroller is, right? So this is what your hardware connection. Whenever there is a person present detected, then give an alarm kind of thing. Right? So now you try to see where it is connected, your PIR sensor. This is digital kind of thing, but analog. You can check it out. So you can check it out. Sensor means temperature or temperature point of view. So that you can try. So this will not work because. So now you can try to see the connections, then working of it. Yeah. So now you try to see where it is connected. So this is an analog sensor. So now it is connected, see here to RA0, AN0. Right, AN0. And the temperature read here can be displayed on the LCD. Right, so their concepts are same as we discussed in 8051 microcontrollers. So the another feature of 16F is parallel slave port mode. So here what you do, to send in a data 8 bits at a time, so then we can, we need from external device, let us take, there is an external device which is sending 8 bits data at a time, or if you want to send data 8 bits at a time. So then that you can try to do with the help of, so port D pins. So port D pins you can make it, 8, by using this you can send 8 bits data at a time in this particular thing. So then here port E, the 3 pins can be used as chip select, read and write. So here, so this is port E. So port E pin you can configure it as chip select. That means when it is 0, right? So when it is 0 and when it is 1 and when it is 0, then you can use the port D pins to write the bits available with this 8-bit microcontroller. So you can write at a time. So port D you can configure it has. So it is parallel slave port, port extension. 8 bits you can send at a time. 8 bits data. So when it is 0 and 1, you can read using port D into it. So this is parallel slave port operation. Parallel slave port operation. And now coming to the PIC16 serial interfaces. Okay, then here you have USART asynchronous link, SPI synchronous bus, and I2C synchronous bus. 3. The serial interfaces facility available with PIC16. So the communication channel, which one you have to use, that depends upon the distance of the nodes. So the distance, if it is 100 meters, then you can use USART. Like if it is within the system design, then we use I2C, integrated circuit bus. Okay, right. So then that depends upon the distance between the nodes and the speed you have to send the data and the number of hardware pins connection. So if it is serial, then the number of pins required would be 1 or 2. Right. So coming to the serial interfaces, now this is what the example you can consider. So the data what you are getting, then you can send through the pins. Right. So here coming to the USART, so this is what your PIC microcontroller, using USART you can send data up to 100 meters with a baud rate of 9600 bits per second. 9600 bits per second, which is around 10,000 kilobits per second. 10,000 kilobits per second, 400 meters range. So the onboard universal synchronous asynchronous receiver transmitter, so it transmits the bits. It transmits the bits using this, then the code. So the logic conversion, it converts 0 and 1 into plus 12 volts and minus 12 volts, and it sends the bits. So example you can find, like you want to let us take a sensor is connected to a microcontroller. You can get the data by using this microcontroller and you can send this to host PC. That example you can consider over 100 meters range. So this is the example. So then at this case, here you can have a line driver interface of MX232 like this here. MX232. So the data sensed by the sensor can be transmitted up to 100 meters by using this USART. So then here you have, ideally it will be 1, then you will be sending start bit, so then the bits, then stop bit. So this is USART standard. This is available with PIC microcontroller. Then next one is SPI. Serial peripheral interface. So in peripheral interface, what it does is, here you have master and then the other devices can be taken as slaves. So the signals available is SD0, SD1 and SCK. So then the timing of this one, so this SCK is your clock, right? And here, so the signals are serial clock, serial data in, serial data out, and slave select on this SBI connection. So it treats the other devices as slave and it selects only one particular device and then it sends the data. This is serial peripheral interface. And then I2C C bus means you have n number of devices if it in a system, so then it sends the data by using I2C C bus. So in I2C C bus, here you have one master, then other things we will consider it as slave. If any device, if it is not selecting any data, so then that particular thing it will be pulled up to 1. It is pulled to 1. Okay, it is pulled to 1. So to send a data byte, the master first sends the control code. So here only thing is the protocol will vary. The protocol differs. So here in I2C bus, to send the data byte, the master first sends the control code to set up the transfer. So then the master, it first sends the control code to set up the transfer. Then the 8-bit or 10-bit address code, each device has to be identified to which it has to transmit the data, and finally the data. So each byte has start and acknowledge bit, and each byte must be acknowledged before the next is sent to improve the reliability in I2C bus. And then these are the I2C signals where you need only 2 lines for transmitting data. And so this is PIC with PC serial port. So this is MAX232 driver. And how it can be connected to 16F877 or 876, you can see. And coming to the interrupt pins, here you have 3 timers, timer 0, timer 1, timer 2, they generates different interrupts. Timer 0 resistor overflow, timer 1 resistor overflow, and timer 2 resistor overflow. So this CCP1 is timer 1 capture or compare detector. So when the timer 1 equivalent compare when it is detected, it generates one interrupt INT CCP1. So 5 interrupts are generated 1, 2, 3, 4, 5 in PIC microcontroller from timers only. And coming to the serial, so when received data is available, transmit data buffer empty to send the data, and data transfer completed, interface activity detected, and bus collision detected. So for these pins, then when it happens in serial communication, so then it generates these interrupts. 16F generates these interrupts. So timers and serial, and coming to the port. So change on single pin RB0, change on any of 4 pins, data received at PSP, write input active, and analog to convert, analog digital conversion when it is completed, it generates INT AD. And analog comparator when it is comparing, analog true comparison happens is what it generates. So these are the interrupts of the ports. And from memory, from EEPROM memory, it generates one more interrupt. So these are the interrupts generated by different devices on PIC16F87. So these are the interrupts you have to know of this particular microcontroller family. So what we have discussed today, so we discussed port pins first, then timer operation next, and then serial communication next, and then the other facility, master slave facility available with, so that you can extend the port pins, right, by this PIC16F77 is what we discussed in this particular class, right? So these are the features, different features available with pick microcontroller, correct. And in detail, if you want to know, if you want to see in detail if this facility is available, so then similarly you can try with of generating different not a particular typical programming is what you can consider, and then here you can generate any one of the signals like this on using any timer or controller of your three timer 0 or timer 1 and timer 2. And if you want to interface a keyboard with which when the key is pressed that has to be displayed on the LCD, that also you can go ahead. So these things you can try. Okay, so and these are general. Once you know the hardware, everything will become very simple. Okay, is it all right? So with this, I'm stopping today's class, and my sincere advice is once you have a strong hardware details of input output devices, it can be extended to any one of the microcontroller, so that only thing is the pin configuration and all will be varying and everything will be safe.